So today we're going to start our discussion of beams, and like we did before for torsion or for 1D mechanics, we're going to start with kinematics. So again, this is how we relate displacements to strains, and it's really all about how the system deforms. And so we're going to start off with a beam, and it's going to look something like that. And we're going to apply some external moments to our beam, call those M. Now, we need some coordinate system for our beam, so X will be along the beam's length, and Y will be pointed down. And when we do that, we're going to see that our beam will deform something like this. And we'll still have our moments on there. It's going to bend. And if we track a little slice of beam, which I'll draw in green here, and we track it to its deformed configuration, what we'll see is that our slice looks something like that. So what's happened is that at the top here, the beam is compressed. So we'll put that as compression. At the bottom here, we've had some stretching, which is tension. And if we have compression at the top and we have tension at the bottom, that means that somewhere in between there must be no stretch at all. And so I'm going to draw that line with my dots here. And it turns out that that location is going to be the centroid of the cross section. And so we'll show that later, but for now I'm going to assert without proof that at the centroid of the cross section we don't have either compression or tension once we're in the deformed configuration. Now, I think the best way to see this is with an example, and I've mocked this up with a piece of celery. You could do it with some other vegetable. Just pick one that's kind of pliable. I like celery because it has lots of horizontal lines, just like our dotted line here. Now you can see I've drawn a bunch of black lines in our celery, and what we're going to do is we're going to try and track those as we bend our celery stalk here. So as I bend my celery stalk, I'm doing the same thing that our moment arrows are in our picture, and although it's hard to see, I think you can still see it a little bit there. So you can see that for the lines that I've drawn, the lines have stayed relatively straight, and you can see that we have a compression at the top of our celery stalk, and we have a tension at the bottom of our celery stalk. And we have this nice deflected curve, and you can see if you watch the lines of the celery stalk, those stringy bits, where those meet our black lines, those have stayed roughly perpendicular to one another. And so by observing some of these deformations and thinking about what's going on here, we can make a couple of assumptions, and then we can work off of those to find our kinematic relationships. So what are the assumptions that we're going to make? We'll put those here. We have a few. The first one is that plane sections remain plane. So that's the green lines in our picture up here. So under deformation, those green lines, they don't warp, they don't get wiggly, they stay straight through our deformation. If we have horizontal lines and vertical lines that start perpendicular here, what we'll find is that they end up being perpendicular down here. So we can say that perpendicular lines, that's an R, perpendicular lines remain perpendicular. Even though in our deformed configuration you can see some of our lines won't be very straight. And the last one is that we'll have elastic or linear materials. That means that we can use all of our constitutive relationships that we've developed before. And the last thing that we kind of need when we're talking about anything, including beams, is our sign convention. So let's draw a little picture up here. This is an important aside here. So this is our internal sign convention. And for our internal sign convention, what we're going to say, this again is just a contract between you, me, and the other engineers, that a positive internal sign is going to look like that. So if we're on the right side of a cut, the arrow is going to point that way. If we're on the left side of a cut, the arrow is going to point that way. And really what it comes down to is if you see a beam that is smiling at you, that's a positive. If you see a beam that's frowning at you, that's a negative. So that's going to be positive. Again, the beam's smiling, that's a negative. The beam's frowning. And so if you can remember those two, you should be good in terms of the internal signs. And so what I want to do to talk about the kinematics here is to think about our little green square, or our rectangle rather. And we're going to say that that has some length, delta x, in the undeformed configuration. And I'm going to draw that picture much larger right about here. Now I'm only going to draw the bottom half of our slice at the top because I want to make sure I can draw it as large as possible. You'll see why in just a minute. So I'm going to draw that to about there, and then I'm going to draw the rest of it with a different color down the page. I'll do the same thing over here. There's the rest of our beam, and here's the rest of our line. Hopefully those are roughly parallel. That's good. And here is going to be our beam. So I said that there's going to be a neutral axis, or a centroid. That looks like that here. We've taken our little slice, so again this is going to be x, and our global y is going to be pointed down. We'll talk about a different y in just a moment. That's going to be our local y for this picture. So now our beam goes under some amount of deformation, and it's going to move down just like it did in this picture. What you'll see is that our neutral axis, our centroid of our section, is going to do something like that. On the left side, our section, which is still going to be straight, remember, might look something like that. And on this side, it might look something like this. And here's it at the top. Might be a little bit curvy. And here's it at the bottom. Again, might be a little bit curvy. And so now we can think about a few different things about our beam here. So this is going to be the direction, or the slope, of our neutral axis at the right end. And this over here will be the slope of our neutral axis at the left end. This is again the line that designates the centroid of the section. The distance from our original centroid to our new centroid, we can say, is going to be v of x, if we assume that x is on the left side. So that is just the displacement in the x direction. This is the displacement in the y direction at x. And on the other side, we can do a similar thing, and we would say that if we come all the way to the centroid here, this is the displacement of the centroid at x plus delta x. Remember that the distance from here to there is delta x, and if you come back to our picture here, the distance from there to there is still going to be delta x, and that's just the distance of the length along our centroid doesn't change. That was our assertion. So now, if we know these are the displacements, we can say something about the slopes. And the slopes would be given by the first derivative of the displacement. So we could say that this is going to be the slope at x, and we could say that this will be the slope at x plus delta x. And if you look at the angle here, and with our yellow line down here, what you'll find is that those are going to actually be the same. So this will also be the slope at x plus delta x. This angle here will be the slope at x. It's just an angle, and we'll utilize that in just a moment. We're also going to define the coordinate system y here. So we're now going to think about y in the deformed configuration, although we're assuming small displacements and small strains, so the difference between these two are going to vanish when we talk about beams in practice. What we want to really think about in our section, again, we're talking about kinematics, so we are interested in strains. And so what we might want to know is if we come down a distance y, let's say, what color would be good? Let's do blue. If we come down to some point here, y, so let's make this some value y, we might want to know what is the strain in our beam at this location. So we know it's going to get longer at the bottom and shorter at the top. So to do that, what we need to know is what is the displacement at y in those two locations. So let's make that orange. So this would be the displacement at the location y at x plus delta x. And the displacement here, this would be the displacement at y at x. Now, if we want to know the strain at that location, all we need to do is subtract our two displacements and divide by the length, which originally was delta x, right? Everything in our beam started out as delta x. So now we could write that. The strain at y is equal to u of y, x plus delta x, minus u, y, and x. All of that over delta x. And now we could start to substitute some things here. What's u of y, x plus delta x? Well, that's going to be here. All that's going to be equal to is our slope, v prime of x plus delta x, times our distance y. So because of the signs, we're going to have to flip a sign here. So it's actually going to end up being negative y, because a positive slope will produce a negative movement. So we have a negative y, v prime of x plus delta x, at the displacement at y at x is equal to negative y. It's still going to be v prime of x. So that's going to be this distance here. Again, if this is a positive slope, it's going to end up being a negative displacement, so we have that negative sign there. And so we could figure out that the strain at some location y is equal to negative y. Now we can put everything else in parentheses. This is going to be v prime of x plus delta x minus v at x. All of that over delta x. And of course, like we always do, we're going to take the limit as all of that approaches 0, as delta x approaches 0, and what we're going to find is that the strain is equal to negative y v double prime of x. And so now, from that, we figured out a relationship for the strain, which is a function of the location in the cross-section, y, and the curvature, which ends up being the derivative of the slope. And so now we can use this to go from displacement, which is v, all the way to strain for a given location y within the cross-section, which means that if we're up here, which would be a negative y, we're going to end up having a compression, and we're going to have for our positive moment here, and if we come down, we're going to end up having a positive strain. We're going to have tension here.